Hello, everyone. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. Today, I am going to discuss about surface area to volume ratio and quantum confinement effect. So, welcome to today's video lecture on surface area to volume ratio and quantum confinement effect. A bulk material is divided into small pieces. The small piece radius decreases. The radius decreases, surface area to volume ratio increases. The increasing surface area to volume ratio gives the different properties to nanomaterials. And also, the bulk material is divided into small pieces. The energy levels also changes. The changing energy levels of nanomaterials gives the different properties to the nanomaterials. Today we are going to discuss about surface area to volume ratio and quantum confinement effect. Factors that differentiate a nanomaterials from bulk materials. So the properties of nanomaterials are very much different from those at a larger scale. So two principal factors are affecting the nanomaterials. The two factors are increase relative surface area to volume ratio, and the second one is quantum confinement effect. These two factors can change the properties such as reactivity, strength, and electrical characterization or characteristics. So, coming to increasing surface area to volume ratio, clearly I wrote here nanomaterials have relatively larger surface area when compared to the volume of the bulk material. You try to understand with an example. Example 1, for a spherical material, let the spherical material radius is smaller. Smaller is the radius of spherical material. So you know very well surface area of the spherical material, that is 4 pi r square. What about that volume? Volume is equal to 4 by 3 pi r cube. So I am taking surface area by volume, surface area 4 pi r square by volume 4 by 3 pi r cube. This 4 pi gets cancelled. In this r square and r cube, some gets cancelled. Remaining, we get 3 by r. So what is this? Surface area by volume is equal to 3 by r. So the bulk material is divided into small pieces. The radius of spherical material is decreases. Then surface area to volume ratio increases. When the radius of sphere decreases, its surface area to volume ratio increases. For a nanospherical material, due to decrease in smaller value, radius value, its surface area to volume ratio increases. What I am saying, the bulk material is divided into small pieces. The radius of that spherical material decreases. Then surface area to volume ratio increases. Increase in surface area to volume ratio gives the different properties to nanomaterials. Different properties to nanomaterials. Coming to second example. For a cubic material, so I am taking here a cubic material. So side of this cubic material, let A surface area 6a square. You can see here this is 1 meter. Let this is 1 meter. Try to understand. So 6 into 1 meter whole square. This is 6 meter square. Surface area 6 meter square. When it is divided into 8 pieces, so you can see here clearly. You can see here divided into 8 pieces. Divided into 8 pieces. So each piece, this is half meter, half meter. So surface area 6 into half meter whole square into number of pieces. So 6 into 1 by 4 meter square into 8. 4 1 ja, 4 2 ja. So 12 meter square. It is divided into 8 pieces. We get 12 meter square. So one piece, this is 6 meter square. 8 pieces, 12 meter square. The surface area is increasing. Coming to another one. So it is divided into 27 pieces. You try to clearly understand here. Yes. So I am dividing into this is 27 pieces. Try to understand clearly. 27 pieces. Yes, 27 pieces. So each piece 1/3 meter. So surface area is equal to 6 into 1 by 3 meter whole square into number of pieces 27. So 6 into 1 by 9 meter square into 27. 9 1 ja, 9 3 ja. So 6 into 3, 18 meter square. So you try to understand for one piece, this is 6 meter square. It is divided into 8 pieces. 8 pieces. This is 12 meter square. It is divided into 27 pieces. It is 18 meter square. The bulk material is divided into small pieces. Small pieces. The surface area is increasing. So nanomaterials are having more surface area. Therefore, when given volume is divided into smaller pieces, the surface area increases. Due to increase in surface area, more number of atoms will appear at the surface compared to those inside. Thus, nanomaterials or nanoparticles have much greater surface to volume ratio. It makes materials more chemically reactive that affects the properties of nanomaterials. The bulk material is divided into small pieces. Increase in surface area to volume ratio. The increase in surface area to volume ratio gives the different properties to nanomaterials. So the bulk material is divided into number of pieces. The surface area of the particles increases. It also gives the different properties to nanomaterials. Coming to surface area to this volume ratio, daily life examples. Crushed ice melts faster than large ice cubes. This is the daily life example. So crushed ice has many tiny particle pieces giving a larger surface area exposed to heat because the volume stays similar but surface area increases. Heat enters faster, causing rapid melting. So, another daily life example powdered sugar dissolves faster than sugar crystals. Smaller particles provide more surface area for a water to interact with, so water molecules break them down more quickly than large sugar crystals with low surface area to volume ratio. Surface area to volume ratio. Another one, finely cooked vegetables cook faster. Cutting vegetables into small pieces increases the area exposed to heat. With a higher surface area to volume ratio, heat spreads through faster, so they cook quickly than whole vegetables. So you see here, ground spices release aroma better. Spices in powdered from allow more surface contact with air and water, releasing aroma and flavor compounds more rapidly than whole spices like cardamom or cardamom sticks. Another one, small soap bubbles create more foam. Many tiny bubbles have more surface area than a few large bubbles, helping them trap more and air and produce more foam while washing. So, coming to another daily life example, powdered coal or charcoal burns faster. Fine powder allows oxygen to reach more particles at once, increasing combustion rate. A large stick has less surface exposed, so it burns slowly. Another one you can see here, breadcrumbs toast faster than a single slice. Crumbs have a much higher surface exposed to heat, so they brown quickly. A whole slice has less area exposed relative to its volume. So you can also see here crackers go soggy faster than bread. So you can see here crackers have more pores and exposed edges, leading to fast mature absorption from air due to high surface area to volume ratio. Various bread stay dry longer. Another one, small animals lose heat faster. Cotton absorb sweat faster than polyester. Tablets work faster when crushed. You see here, dust particles may explode in factories. Hot tea cools faster in a wide cup. A wide cup exposes more surface area to air, allowing heat to escape more rapidly. A tall, narrow cup cools slowly because of low surface area exposure. Cloths dry faster when spread out. So 14th one, you try to see here. Drying clothes over a wide area increases exposure to air and sunlight, increasing evaporation rate compared to folding or stacking. Yes, the thin noodles cook faster than thick noodles. You try to understand. So skin related in water, wrinkles in water, salt granules dissolve faster than rock salt, and butter melts faster when spread thin. Ice cream melts faster in a smaller scoops. Cells in living organics stay small. These are the surface area to volume ratio daily life examples. What are the applications? You try to understand here. Surface area to volume ratio, what is the application? So, tablet and medicine, you try to understand here. Medicines are often powdered or made into small granules to increase surface area to volume ratio. More surface contact with digestive fluids allows faster dissolution, dissolution, and quicker therapeutic action. So, daily life applications for surface area to volume ratio, catalyst in chemical industries. So, catalysts are made with porous or nanostructured surface to increase in surface area to volume ratio. A larger reactive surface speeds up chemical reactions, saving time and energy in industrial production. Nanomaterials for sensors and electronics. Nanoparticles have extremely high surface area to volume ratio. It is making them very sensitive to small chemical or electrical changes. This property is used in gas sensors, biosensors, and nanoelectronics. So, coming to another application, solar cells efficiency improvement. So solar cells use nanotextured or rough surfaces to increase surface area to absorb more light, improving energy conservation and efficiency. So you see here artificial lungs and dialysis mechanisms or missions. Dialysis membranes and artificial lungs use thin, high surface area layers to allow rapid exchange of oxygen, carbon dioxide, and waste substances across membranes. So, food drying and dehydration. Food industries slice fruits into thin pieces before drying to increase surface area, speeding evaporation and preventing microbial spoilage. You see here heat sinks in computers, cooling towers in power plants. These are also applications you try to see here. So you see ninth one combustion of fuels, air filters and water filters. So filters use thin fibers and porous materials with a high surface area to trap more dust particles or any other related, increasing filtration efficiency. So number of applications you can see: fertilizer, granules in agriculture. So metal crystallis in automobile exhaust systems also. So oxygen absorption in fish gills and human lungs. So ice cubes in restaurants. So crushed cubes drinks faster due to increased area touching the liquid, saving time and preserving behavior temperature. So another one also you see detergent powders for cleaning, blood capillaries in human body. So spray, painting and perfume sprays, activated charcoal for poison treatment. So microbial growth in anything related. So here biomedical drug delivery using nanoparticles. So these are the very important applications to surface area to volume ratio. Surface area to volume ratio. Again, try to understand surface area to volume ratio in simple. Let us consider a sphere radius or surface area 4 pi r square, volume 4 by 3 pi r cube. So surface area to volume ratio we get 3 by r. So bulk material is divided into small pieces. The radius of sphere decreases, then surface area to volume ratio increases. When the radius of the sphere decreases, its surface area to volume ratio increases. For a 1 cube volume, 1 meter into 1 meter into 1 meter, that is 1 meter square, that is volume. It's the surface area of the cube, 1 meter into 1 meter into 6 spaces, 6 meter square. So for this bulk material, we can also try to understand in this method. When the same cube is divided into 8 pieces, one piece half meter into half meter into 48 faces. So 48 by 4, we get 12 meter square. When the same cube is divided into 27 pieces, its the surface area 1 by 3 meter into 1 by 3 meter into 162 faces. So 162 by 9, 18 meter square. We can also understand in this process. So this 1 meter square, this is 6 meter square, this is 12 meter square, this is 18 meter square. The bulk material is divided into number of pieces. The surface area of the nanomaterial is increasing. Therefore, we found that the given volume is divided into smaller pieces. The surface area increases. Hence, as a particle size decreases, a greater proportion of atoms are found at the surface compared to those inside. Example, a particle of size 30 nanometers has 5% of its atom on its surface. At 10 nanometer has 20% of its atoms, and at 3 nanometer has 50% of its atoms. We can understand easily. Thus, nanoparticles have much greater surface area per given volume. So, compared with larger particles. Yes, coming to second one, quantum confinement effect. So, the properties of materials can be studied based on their energy levels. Based on their energy levels. So, bulk material, when atoms are isolated, energy levels are discrete energy levels. For isolated atom, these are the discrete energy levels. Discrete energy levels. When atoms are isolated, the energy levels or discrete energy levels are discontinuous. For materials consisting of large number of close atoms, the energy levels split and form band. Here, for bulk material, these are having band type of energy levels. Energy levels. But nanomaterials are having intermediate energy levels. Nanomaterials are having intermediate energy levels. When the material size reduced to nanoscale, energy levels of electrons changes. The energy levels changing effect is called quantum confinement effect. This effect is called quantum confinement effect. This affects the optical, electrical, and magnetic properties of nanoproperties. So the properties are changing due to the changing of the energy levels. For isolated atom, you see here, for example, this is the isolated atom. This isolated atom has the energy level E1, that is a discrete energy level. The atoms are brought too close to each other. For example, you try to see this is one atom, this is another atom, brought too close to each other. So two atoms has E1 and E2. If number of atoms we are taking E1, E2, E3 and so on, the energy levels form like a band. The bulk materials are having band energy levels we can observe. So the bulk material is divided into up to nanomaterials. The energy levels are changing. These energy levels are intermediate energy levels. The bulk materials are divided into nanoparticles. The energy levels are changing. When the material size is reduced to nanoscale or nanomaterial, energy levels of electrons changes. This effect is called quantum confinement effect. The quantum confinement effect change the optical, electrical, and magnetic properties of nanomaterials. So coming to see here, quantum confinement, daily life examples. So quantum dots, you see, are QLED TVs. Quantum dots emit very pure and bright color when excited by light because of quantum confinement. Changing the nanoparticle size changes the color displayed on modern Q light emitting diode screens. Coming to second one, daily life example. So blue and red light emitting diodes are laser color from nanoparticles. Semiconductor nanoparticles are engineered so that smaller particles emit blue light and larger ones emit red light due to band gap change caused by confinement, quantum confinement effect. So you see here fluorescent nanoparticles in bioimaging. Doctors use quantum dots as fluorescent biomarkers. Their color depends on particle size, helping visualize cells and disease with high clarity. So another one daily life example, sunscreens using titanium dioxide and also zinc oxide nanoparticles. When titanium oxide and zinc oxide is nano-sized, the quantum confinement effects alters light absorption, making sunscreen transparent while still blocking ultraviolet rays. So security link in currency notes. Quantum dot ink glows in different colors under UV light because quantum confinement changes their emission wavelengths, preventing counterfeit. You see, quantum dot sensors. Smaller confined quantum dot particles respond strongly to chemicals or gases and are used in pollution detection and breath analyzers. So another daily life example you can see nanoparticles in LED Christmas lights. So color variations and high efficiency at a small size are due to quantum confinement, tuning the band gap. Nanoparticle based strain resistance clothing. You see here memory chips and storage devices. Modern flash memory uses quantum confinement effect in extremely thin layers to confine electrons. So storing bits on as charge levels. You can see here mobile phone displays and cameras. Quantum dot image sensors in smartphones capture more light with less energy due to the quantum confinement, improving electron hole separation. Biomedical cancer treatment, quantum dots for targeted therapy. So, nanoparticles enter cancer cells and glow under imaging because their optical properties depend on quantum confinement. So, laptop and EV batteries, nanoscale materials in anodes or cathodes provide better connectivity and charge storage because electron pathways change due to the quantum confinement. So, you can see nanoparticle based toothpaste, antibacterial bacterial silver nanoparticles in band gauge. So, photocatalytic water purification, semiconductor nanoparticles like zinc oxide, titanium dioxide have increased catalytic power at a nanoscale because quantum confinement widens the band gap and improves reactivity. So, fiber optical telecommunications. So, quantum confined effect we can observe in semiconductor devices. These are used as amplifiers and lasers that control light signals more efficiently. So you can see here glow in the dark toys, car headlight, street lights, products with nano pigments, thin film, transparent screens. So these are the daily life examples of quantum confinement effect. So try to understand the quantum confinement effect applications. Quantum dot display and QLED. The quantum confinement effect we can observe in Q light emitting diode TVs. Quantum dot changes color depending on particle size. This property is used to produce highly pure red, green, and blue light, giving TVs higher brightness, wider color range, and better contrast than conventional displays. You see here solar cells and photovoltaics we can observe. So quantum dots absorb sunlight more efficiently due to tunable band gaps. By adjusting particle size, solar cells capture a broader range of wavelengths, increasing energy conversion efficiency. I wrote here clearly. Bioimaging and medical diagnostics. The quantum confinement effect influences the bioimaging and medical diagnostics in different colors depending on particle size. Doctors uses them to tag cells or tumors for high resolution imaging. It is helping to doctors to detect diseases early. Targeted cancer therapy. So the quantum confinement effect is using in targeted cancer therapy. Quantum dots can attach to cancer cells and it releases drug molecules selectively. Their optical properties helps locate cancer cells and monitor treatment progresses. The quantum confinement is very useful to doctors in treatment of cancer therapy. So coming to this light emitting diode and laser technology. The quantum confinement effect is used in LED and laser technology. So by controlling nanoparticle particle size, LED and laser emission colors can be precisely tuned. So it gives more efficient, brighter, and longer lasting light sources. Quantum dot photodetectors. The quantum confinement effect we can observe in quantum dot photodetectors. So this effect gives the particles improved sensitivity to light. They are used in night vision cameras, security systems, and scientific instruments for detecting weak signals. You see here catalysis in chemical industry. Nanoparticles have high surface area, enhanced electron mobility due to quantum confinement, speeding chemical reactions and reducing energy consumption in industries. So quantum confinement effect is very useful in catalysis in chemical industry. So coming to this water purification using photocatalysis. Quantum confinement effect using the titanium dioxide and zinc oxide nanoparticles. Quantum confined effect is used in titanium dioxide and zinc oxide nanoparticles, break down pollutants under UV or sunlight. This helps in removing organic contaminants and disinfecting water. So coming to memory storage, flash, SSD, qubits. So the quantum confinement effect is also used in flash, SSD, qubits, that is memory storage related. Quantum confinement in ultra thin layers traps electronics in discrete energy levels, allowing high density and fast digital storage technology. You can see here another application, quantum dot biosensors. Quantum dots detect toxins, viruses, or glucose levels by changing their fluorescence when interacting with specific molecules used in medical and industrial sensors. So, it is also helpful of quantum confinement effect to quantum dot biosensors. Bacterias and batteries and supercapacitors. You see here, we discussed about virus, bacteria, everything in quantum dot biosensors we can observe. But here, 11th one is batteries and supercapacitors. So nanostructured electrodes improve ion transport due to confinement effect, enabling faster charging and higher energy storage for electric vehicles and electronics. Coming to 12th one, transparent and flexible electronics. The quantum confinement effect is used in transparent and flexible electronics, that is, quantum confined layers enabling thin film transistors for foldable displays. So, security ink for anti counterfeiting. So, quantum confinement effect is used in antibacterial coatings and medical band gauges. Silver nanoparticles release ions faster at nanoscale due to confinement, providing stronger antimicrobial activity in wound dressings and coatings. So here also you try to understand here cosmetics and skin products. Nanoparticles enhance UV, that is ultraviolet absorption and light reflection due to the quantum confinement, improving sunscreens, whitening creams, nail polish, and lip colors. In everywhere, the quantum confinement effect is they are using. The quantum confinement effect is used in high resolution optical microscopy. So quantum dots acts as bright stable markers in super resolution imaging, enabling visualization of molecules beyond the limits of normal light microscopes. So you can see here quantum dot sensors for environmental monitoring. The quantum confinement effect we can observe in quantum dot sensors for environmental monitoring. So changes in electron behavior under confinement enable sensing of gases like nitrogen dioxide, carbon monoxide, and humidity for smart pollution monitoring system. So you see here optoelectronics and fiber communication systems. The quantum confinement effect is used in optoelectronics and fiber communication systems. Quantum well and quantum dot lasers are used in fiber optic communication because the quantum confinement increases efficiency and reduces power requirements. Thermoelectric devices. The quantum confinement is used in thermoelectric devices. Quantum confinement increases electrical conductivity and reduces thermal conductivity, enhancing devices that convert heat into electricity. This is the very, very important application for quantum confinement effect, that is thermoelectric devices. Coming to this energy efficient window coatings. The quantum confinement effect is used in energy efficient window coatings. Nanoparticles based coatings change their optical properties depending on light and temperature, improving indoor cooling and reducing electricity uses. Yes, so you see here the quantum confinement effect is observed when size of the nanomaterials too small to be comparable with wavelength of the electron. So as the size of the particle decreases till we reach a nanoscale, the decrease in confining dimensions makes the energy levels discrete. And this increases of the band gap, and ultimately the band gap energy also increases. Since the see here, band gap and wavelength are inversely related to each other. The wavelength decreases with a decrease in size, and the proof is the emission of the blue radiation. You can observe in that figure. You try to understand. The quantum confinement effect is observed when size of the nanoparticles too small to be comparable with the wavelength of the electron. The particle size changes, the wavelength also changes. The changing wavelength gives the different color. Since band gap and wavelength are inversely related to each other, the wavelength decreases with a decrease in size, and the proof is the emission of blue radiation. So, summary, try to understand here. Surface area to volume ratio. You can see here, as the size of the object decreases, its surface area becomes larger relative to its volume. The bulk material is divided into small pieces. The radius is decreasing. Then surface area to volume ratio increases. Increase in surface area to volume ratio gives the different properties to nanomaterials. So, higher surface area to volume ratio allows faster heat transfer, reaction rates, cooling, melting, dissolving, drying, and absorption we can observe. So, very important in daily life and industry and biology related we discussed in this video. So, the bulk material is divided into number of pieces. The surface area also increases. Surface area also increases. The nanoparticles are having large surface area. The large surface area gives the different properties to nanomaterials. The bulk material is divided into small pieces. The nanoparticles gets large surface area. The spherical nanoparticle radius decreases. Surface area to volume ratio increases. So due to the large surface area and increasing surface area to volume ratio gives the different properties to nanomaterials. Nanomaterials. Due to this increase in surface area to volume ratio, we observe the faster heat transfer, reaction rate also increases, the cooling time also we can observe, melting point also changes, dissolving, drying, and absorption, everything will be changing. So, very important in daily life applications we studied in this video. The applications and biological industry applications also we studied in this video. So quantum confinement effect. When material size becomes extremely small, electron motion gets restricted. This creates discrete energy levels causing properties like color, conductivity, magnetic behavior, and optical emission to become size dependent. We discussed in this video. So isolated atom has the discrete energy level. The bulk material has the band gap or band energy level. The nanoparticle has the intermediate energy level. The bulk material is divided into up to nanomaterials. The energy levels are changing. The changing energy levels gives the different properties to nanomaterials. Effect is called quantum confinement. The changing energy levels, changing the color, changing the conductivity, magnetic behavior, and optical emission to become size dependent. So we discussed about surface area to volume ratio, daily life examples also we discussed, applications also we discussed. That quantum confinement effect, daily life examples we discussed, and also uses in QLED TVs, bioimaging, solar cells, lasers, sensors, memory devices, and medicine. So, the quantum confinement effect, daily life examples we discussed, and applications also we discussed in this video. Yes, the daily life example we discussed in this video. Crushed ice melts faster than ice cubes because of increase in surface area to volume ratio. So powder dissolves faster than crystals, more contact area. That is also surface area to volume ratio. Wet cloths dry faster than when spread. It is also increase in surface area to volume ratio. Sunscreen with nano zinc oxide becomes transparent. Quantum confinement, this is the quantum confinement effect, controls light absorption. Currency security ink glows in multiple colors depending on quantum confinement. effect. So we studied the applications also in this video, quantum dots for displays, sensors, solar cells, etc. Nanoparticle catalysts with high surface area to volume ratio for faster chemical reactions we discussed. So medical imaging and cancer therapy using fluorescence from quantum confinement effect, that is quantum dots. Batteries and supercapacitors using nanomaterials for fast charge transparent transport. We discussed using the quantum confinement effect. So in this video, we concentrated on increasing surface area to volume ratio, how the nanoparticles properties are changing, daily life examples and applications we discussed. In quantum confinement also, we discussed in this video clearly the daily life examples, how the nanomaterials are affecting due to the quantum confinement effect and their daily life examples and applications also we discussed in this video. Thank you so much for observing this video. Thank you. Thank you so much.